Hello everyone, welcome to session 3 of the Shimadzu LC Purification series. My name is El McCoy. I'm a technical specialist in the LC technical team at Shimadzu UK. This series is designed to introduce you to and increase your knowledge of LC purification. This third session in the series looks specifically at semi-preparative LC scale purification. The Shimadzu Purification webinar series consists of 3 sessions. The first covered the fundamentals of LC purification and included the subjects: what is LC purification? How much sample can you expect to purify? Upscaling basics, recycling and concentration. This session is available on demand through our website. Session 2 covered the difference between semi-micro and analytical scale purification, principles specific to semi-micro and analytical scales, things to consider at these scales, instrumentation and software advantages. This session will also be available on demand through our website. Today's webinar, session 3, will cover principles, common issues, tips and tricks of semi-preparative scale chromatography, UFPLC, ultra-fast preparative and purification LC, and lastly, semi-preparative SFC scale purification. A quick session recap. In session 1, we said preparative LC is concerned with physically separating and isolating an amount of one or a number of components in a sample. We discussed the relationship between purity, yield, and rate. We looked at the effects of flow rate, scaling, large volume injections, particle size, and peak recycling techniques. In session 2, we defined semi-micro and analytical scale purification. Semi-micro considerations were challenges of low volume collection, peak noise rejection settings, fraction tracking, and mobile phase monitoring. Analytical considerations: purity, upscaling, peak collection modes, different detectors, and how practical they are to use for purification, and the need for preparative flow cells. Scale, loading, and flow rate of columns from semi-micro to preparatives as an overview. This was covered in sessions 1 and 2. In this webinar, however, we will turn our attention to semi-preparative scale solutions. Let's begin. Session 3, Semi-preparative LC Purification. As a chemist performing purifications for your compounds, the goals for your purification will likely be something like these. Purity must meet your target, for instance 95%. You must be able to purify enough material for your next step. The materials should be delivered in as concentrated a form as possible to prevent more processing. The material should be in your chosen form, for example, an alternative counterion. Collection and recovery from the machine should be greater than 90%. And finally, the equipment must be reliable, rugged, and easy to use. As we discussed earlier, LC purification is a great tool. It does, however, have some limitations. We've been listening to our customers and have worked closely with them to come up with innovative solutions that deal with the most pressing common issues. These include reducing the water content of fractions generated by purification so reducing time-consuming evaporation steps. Removing buffers and salt forms. Increasing speed of purification. And finally, improving the purity of fractions. Here we present 3 different approaches to semi-preparative scale purification. Each one has its strengths and weaknesses. Firstly, classical semi-preparative LC purification. Secondly, UFPLC, ultra-fast preparative purification LC. And thirdly, semi-preparative scale SFC. We will now start with classical semi-preparative LC purification. Please note that many aspects of purification have been already covered in sessions 1 and 2. This session will therefore cover relevant items not already covered. Semi-preparative LC purification can be defined in terms of scale to use 20 mm ID columns at approximately 20 mL a minute and is capable of purifying up to 200 milligrams of material. Systems are often used to purify target compounds from unwanted reaction products, impurities, and starting materials in reactions. There are 2 approaches to system design. If sample purification workload is high and there is no limit on space, then a dedicated system makes sense. Analytical scout runs would be completed on a separate analytical system. If the preparative workload is not so high and space is at a premium, a combined system can then do analytical screening, analytical scouts prior to purification, the purification of the samples themselves, and then purity checks on the actual fractions. Here is a simple schematic of a purification system. Mobile phase flows from the bottles, through the pump, through the preparative mixer, through injector, onto the column, onto the detection system, and finally onto the fraction collector. We covered the different detection modes in session 2. Now we add in MS detection. It allows us to collect based on mass spec where UV response is low. The example on the right goes a step further, however, and shows high purity collection of target components that are not completely separated by using 2 MS signals. Peak collection by LCMS plus UV. Advances allow peaks to be collected using signals from varying detectors to improve purity. The target product is partially coeluting with byproduct. The fraction that has been collected by using only MS triggering provides high recoveries but can be contaminated. Combined triggering can detect the inflection point based on the UV trace, and fraction purity is increased. The residual fraction is collected into the following fraction tube. To run the LC or SFC in an open access environment, users log in, add their sample. Once the run is completed, the user receives an email with a link and they can review the data at their desk. Using the same open access software, we employ an algorithm for compound isolation and purification. ACEPrep initially verifies the retention time of the target compound using the analytical scale LC data. The retention time of the target compound is then used by the ACEPREP algorithm to calculate the focus gradient profile for the preparative scale separation to deliver the highest purity and recovery of the collected LC fractions. What happens if something goes wrong? Can you recover your sample? If a problem occurs before injection, sample can be collected into a specified recovery vial. If the error occurs after the sample has been loaded onto the column, the sample can be recovered into a bottle. Software benefits. Mobile phase monitoring. Ensuring sufficient mobile phase is available using gravimetric balances, even with large bottles up to 5 litres. Automatic peak recognition. The fraction collector is able to collect the peaks based on the detector signal reliably. Fraction simulation uses a scout run to predict collection parameters. Easy as clicking and dragging. These 3 features were covered in session 2. Fraction collection based on multiple signals to improve collection purity using UV and MS signals for increased purity. Open access software using a generic gradient to create a specific focus gradient for the target of choice. And finally, emergency sample recovery. Summary of semi-preparative LC purification. The positives. Covers a wide range of compounds, including proteins and peptides. Many modes of separation are available: size exclusion, ion exchange, normal phase, and reverse phase. Generally, LC has good chromatographic performance and good loading on column. The negatives: the collected fractions typically have a high concentration of water. Also, as a result, fractions typically are very dilute, and hence long evaporation times post-purification. The salt form is determined by the mobile phase. UFPLC, ultra-fast preparative and purification LC. This offers fast recovery of highly purified target compounds in a simple workflow by automation of collection as well as normal LC, but further adds concentration, purification, and recovery. This is a schematic of how it works. Sample will be injected. Separation will take place on the preparative LC column, and the compound is isolated and concentrated. A washing step will then remove the TFA or buffers from the trapped compounds, also removing any water that was present. The target compounds can then be eluted with organic solvent as a concentrated band, leaving a highly pure target in organic solvent. High-speed concentration of cyclosporin A. After the separation, the target compound fraction is injected into the trap column, enriched by trapping and eluted by an organic solvent. This enables recovery with a small volume of liquid, so subsequent evaporation can be performed in a short time. In this way, the same mass of sample can be purified in a shorter time versus elution in reversed phase conditions. Removal of ammonium chloroacetate salts from ibuprofen. Ibuprofen the target component, is cleaned by retention on a trap column. As a result, the ammonium chloroacetate salts contained in the mobile phase solvent were removed by rinsing the trap. This prevents the retention of salts in the mobile phase solvent during evaporation, so that only the target component is recovered when eluted. Dedicated software makes using the system very easy. You can clearly see the chromatogram and the peaks that have been collected. The trap columns are color matched with the peaks selected. The elution chromatogram is also color coded, along with the collection vessels. UFPLC. Positives. Fractions are much more concentrated. Fractions are in organic solvent and the aqueous has been removed. Our compounds can be converted to the desired base form if needed. Good loading on the enrichment cartridges is possible, even up to 300 milligrams. Fast speed compared to LC plus the evaporation step. Flexible and easy to use software. Negatives. The range of compounds is not as wide as standard LC. Only tested with reverse phase chromatography so far, and a limited number of peaks can be trapped. Which brings us lastly to semi-preparative scale SFC purification. Advantages of preparative SFC compared with preparative LC. Shorter run times. This is due to the higher flow rate capability due to the lower viscosity of CO2 and its faster mass transfer. The runtime is 3 to 5 times shorter than preparative LC, especially for chiral separations. Reduction in organic solvent consumption. The primary mobile phase is CO2, so less organics are used in comparison to normal and even reversed phase. Shorter dry down times, simpler post-processing. Preparative LC, longer dry down times, especially when the primary mobile phase contains water. Preparative SFC has shorter dry down times because the CO2 is vaporized during fraction collection. If we compare an equivalent Prep LC, this would be the typical schematic. By swapping the aqueous for a CO2 bottle and adding a back pressure regulator and a high pressure flow cell, finally a makeup pump and a gas liquid separator, we have a Prep SFC system. Some SFC systems have the injector in line with the organic modifier. However, sample cannot then be injected at low or 0% modifier concentrations. Early eluting volatile components may need separation at lower modifier concentrations, for example 5% or lower. If this is the case, the on-column dilution injection method works much better. Back pressure control is the Achilles heel of many SFC systems. With this new low volume, easy to maintain design, stable back pressure control is achieved and maintained, as you can see from the flat pressure trace. Previous generation separators are prone to carryover and low recovery. The innovative Lotus Stream gas-liquid separator overcomes these issues with an elegant and efficient solution. This can clearly be seen in the videos with no GLS compared with the Lotus Stream. Note that both are flowing at 100 mils a minute. The clear benefits of its design can be seen in these results, with the volatile compound linalool recovery being clearly superior and with better relative standard deviation. Two configurations are available. One for stacking fractions, aimed at repeated fractionation of a few target compounds, such as chiral compounds. And one for multi-fractions, best used for collection of achiral compounds and active ingredients in natural products. The software was designed with the collaboration of the Enabling Technologies Consortium, ETC, to be compatible with their members' workflow. In order to do the scouting for preparative SFC, an analytical system is needed. If not all your compounds are suitable for SFC, having an analytical system which can scout for both LC and SFC would be useful. This system allows seamless switching to facilitate this. If you're only occasionally needing to purify small amounts or just want to purify an unknown peak of interest, analytical scale SFC purification does offer some advantages. Analytical runs and small-scale purifications can be done on the same instrument. This also can offer better resolution than LC for many compounds. SFC typically offers better loading on column than LC. You can therefore get better throughput. This can be similar to a semi-preparative LC system as a result of better loading and speed. By simply adding a fraction collector to a Nexera UC system, the Lotus Stream's fine control of gas-liquid separation means collection even into 2 ml vials is possible. A summary of semi-preparative SFC purification. Here are the positives. Covers a wide range of compounds. SFC offers excellent chromatographic performance. Typically faster cycle times, excellent loading on column, and the collected fractions typically are in a high concentration of organic with no water. Hence, less evaporation time is needed. Excellent recoveries also of very volatile compounds. And it's easy to clean and maintain its components. The negatives? The salt form is determined by the mobile phase. This could be overcome with a modified makeup additive. A CO2 infrastructure is needed. So to conclude, we've discussed the merits of the three alternative solutions, and now we can see that classical semi-preparative scale LC is a versatile tool, but it often leaves us with dilute aqueous fractions in a salt form that we may not want, giving us delays after the run to concentrate our fractions. UFPLC does answer some of these issues by giving us concentrated fractions in organic solvent, saving dry down time, and we also get our compound in a salt form that we can choose with increased purity. SFC also answers some of these issues by giving us concentrated fractions, free of water, with a higher speed, gives us excellent recoveries even with volatile compounds, but it does need a CO2 infrastructure. You can find us on all the usual social media platforms. Please feel free to contact us should you wish to find out more. As we close this series, thank you very much for your participation. We hope that you found these sessions useful and enjoy the rest of your day.
Excellence in science. Shimadzu.